Welcome back. Next one is the software belt. We are still going back to the 5G Atom. And what you see now, after we have introduced the technical requirements and the concept, the question is, how can we realize such a concept? Mobile edge cloud sounds very interesting, but how can something like this be realized? And here the yellow parts are the technologies, also called the software belt, where you see we have something called SDR, which is software defined radio, which is a software defined realization of the air interface. What is good for the air interface is also good for the core network. And we have software defined networks. And inside the software defined networks, we can run network function virtualizations, which is nothing else than apps that you normally would put on mobile phones. Now you can install anything you want inside your network. That's very good for network operators. And in order to make these two things very efficient, we need service chaining function technologies for that. Okay, this interesting part here is that most of the stuff is open source. And so everybody of us could now just download something and start to become a software deliverer for network operators and to give software solutions, right? And as everybody can do it now, the question is, what makes a product? First of all, testing. So the product must be failure proof so that the network operators will not suffer by restarting it over and over again. And you would like also to have some novelty into that. But before we go into that, let me just describe a little bit these 4 bullets here. The software-defined radio is an interesting concept. It's a little bit older. What you can see here is the reuse of hardware components was the first idea, and later they came to flexible control of the components. So here you see a software-defined radio with a normal RF baseband part, and then you see that you can have some parts of that in software. That was very important at the time that they introduced 3G, because when you had different bands on a global spectrum region, then you don't want to implement it 12 times. You just maybe want to change the filter banks, right? So software became already introduced here in software-defined radio. Nowadays you can get way better software radios. There are some old GNU radios. National Instruments has some that we also have here in the lab. But with a Kickstarter project, the Lime SDR was quite interesting. It only cost $99. And with that, you can do a lot of good things, right? You can build a Bluetooth device, you can build a Wi-Fi device, an LTE device, just by changing the software on top of it, right? And this is interesting for our projects, for something to create low latency, to bring in some new technologies. There are a lot of projects currently we are running with this technology. Then later, as I said, it also became, the software-defined came also into the networks. But in the beginning, it was not called SDN, they were called active networking. So the idea is, can I change with software the protocols? And it's exactly the same what we do in SDN and NFV, but at that time, it was a nice way to have very easy testing, right? For example, security protocols could be changed, complexity could be looked at. We made one project, for example, where we had a mobile device and an internet server, and if the mobile device, a lightweight device, would then have a TCP connection, the TCP connection was quite complex and was using a lot of energy. So in order to make this more lightweight, what we did is we just moved the TCP and IP protocol suite to a gateway, the access point, and then from there on used a lightweight protocol, right? And with active networking, we could select both situations. If you then look at the energy consumption over the number of flows, not so important here, but you see already if you would have the state-of-the-art TCP protocol stack on the device, you would use more energy than if you have this kind of lightweight protocol. And this active networking was there for a while, but then nobody looked into this. The reason was that nobody in industry really cared. You could do that, but there were no devices really able to implement this. This changed with software-defined networks. For example, Cisco was one of the first companies that introduced SDN also for their switches. So now you could really change something on software on their devices. And so all this theory that was acquired with active networking came back. If you look into these two things, what is software-defined networks and network function virtualization? Um, Loosely speaking, software-defined networks is a very centralized way now to make the switches to let them know which routing path we would like to do. It has a very good way to design the network. Where on the network function virtualization, this is more like app style, where you have a function, a network function that you can place within the network at a given point. So both of them are addressing a field that you can enable very fast your experience now with new ideas. While normally when you have a new idea, you need to write papers, patents, then you go to standardization meetings, and if you are lucky, after 10 years, 20 years, the industry will take your idea. Now you have an idea, you can implement it very fast, right? And you don't have this long-lasting standardization process anymore. And you can even optimize or parameterize with the central control all of the features in your network. So again, when you understand that the telephone networks had a centralized concept and the internet was fully distributed, here we have a middle way. So we have a centralized controller that will tell the switches what to do. It's not that they find it out in a distributed fashion. So with that, we can deploy new functions really in no time, and this also contributes to the things we have said before. We don't have to wait every 10 years for new hardware. Here we can do it on a daily basis. The NFV component is really that you have more advanced network functions, and you can place them on generic hardware. And therefore, you don't have to buy dedicated hardware. You can just have generic hardware. This is called commercial off-the-shelf things, and they are way cheaper than other things. Now you can reallocate functionality, or you can even spawn new functionality at certain elements in order to increase the network performance, right? As we have seen, network latency capacity. And here you see already, if you want to do a mobile edge cloud, or if you want to do the network slicing, these two elements are the ones that you will need. And in this lecture, we will learn about how to do this. Also here, new functionality can be deployed in nearly no time. That is exactly what also SDN has in the motivation. You can see it also in a different way. When you have seen how computation and communication was in the past, that led now to new principles for software networking, right? I have a picture for that. Here you see communication was the telephone, and computation was done on here in a Commodore 64, not so much. But nowadays, all of that communication and computation is in one platform, right? And if you go back, the NFV was then more motivated by the timely deployment and financial gains and that the network operators ask for, because they were threatened by OTT providers that could very quickly change the services on the end device and also on the cloud in the back end. And they were just the ones, the pipes that dump in a dump pipe and passing bits from A to B, but they could not create new services. And in order to be also able to create new services, they needed this SDN NFV for that. Sometimes you see that they are often intervened. So there are two different groups in the IRTF that are discussing this momentarily. Okay, that we had already. So the benefit and promises is then really to have a reduced equipment cost, right? They call it sometimes CapEx, right? And this is that you don't need so many specialized hardware. You can have one generic platform. You can even put more of the function on the same generic platform, and you can even scale nicely. So you can start very slowly investing as much things as you need throughout the build-up of your network. This increased speed to the market is, as I said, also a result of the OTT threatening, and this is minimizing this network operator cycle of innovation. because they are waiting for new stuff coming from the manufacturers, and they wait for something that is in standardization, etc., etc., etc. So also the availability of network appliances in multi-version and multi-tenancy, which allows for a single platform for different application users and tenants, which is really good to reduce the prices, of course. And it also enables a variety of ecosystems where you open it to other people to build up their own NFV components. And with that, of course, you encourage even your own team to come up with new innovations. Even the team is not waiting for the standardization outcome. They can do it on their own. So the flexibility and the rapid deployment, I already mentioned that. The improved operational cost is something. The software-oriented innovation is part of the benefits and promises. But the only, and then you have the service differentiation and customization with reduced OPEX. Before that, we had the CAPEX, which means that over the time you run the network, you also can reduce the cost by understanding which parts are needed and when they're needed. Some of them you can switch off overnight. And what you need now, you don't need specialized skill sets from an applicant. What you now need is an IT-oriented skill set and talent, nothing else. Somebody who can program and has an understanding of communication networks is good enough to go.
My name is Robert Schmoll.
So that you can really implement this, there was a demonstration here with Ericsson, and we implemented a form of coding in the network, where you see here two screens with very good video. You can switch now the kind of transport like store and forward with compute and forward, but I leave it up to you to go to the YouTube page to look into that, right? Here you can see how he's changing the parameters on the fly, and everything what he's doing here on the display is happening down here in the box. And you see already the video is degraded, so a very interesting approach. Listen into the video. Last but not least, in order to increase the speed, then we have to look into something that is called service chain function. There's a paper that we have recently published in the JSAC, and what it does is it looks into the problem of virtualization. So virtualization is opening the door for a mobile edge cloud. So this is good. It seems that this is the way how we get latency under control, right? The problem is, once we open the box of Pandora with virtualization, every time we're using it, we are also adding some sort of latency. What you see here are 3 or 4 curves. The black dashed line here is not really a curve, is exactly the 35% of the millisecond I was speaking before. So you would like to have your latency on the left side. But when you're using a mobile edge cloud on that, depending on how you do this, the latency can go up even over a millisecond, up to several tens of milliseconds. And this is because of the virtualization, which means if packets arrive, they're now not on hardware level just forwarded. Now they go up to the virtualization box, and even if you just would push them down again without doing anything with the packet, what you see here is this is the minimum what you can get. So what we have achieved is the green line by using service function chaining, also something that you will see within the lectures later on. Okay, now that leads us to the last tier, which is the 5G novelty and innovation.